So, we are continuing with the metal forming module of this advanced manufacturing and process modeling course. So, till the last class we have discussed about different forging processes, and also we have discussed about how the dislocation flow of dislocation decides on the deformation behavior of various metals. We have also discussed about different kind of dislocations, twins, and also the shear plane, shear direction, etc. So, now we will go deeper into the mechanics associated with the forming, forging as well as rolling and other processes. So, today in this class we will start with the introducing the problem for forging in plane strain. So, so forging stress analysis in case of a plate we will discuss. So, you can see the schematic over here. So, it is the figure represents stresses during forging of a plate under plane strain conditions. So, why plane strain? Because there is no strain in the width direction. So, there is only strain in two directions. So, we will discuss in detail about that. So, the plate has a constant thickness throughout the process, and lateral flow and frictional forces. So, lateral flow, metal flow occurs perpendicular to the ram's travel direction. So, ram is traveling in downward direction. So, the lateral flow will happen perpendicular to that. So, basically it is kind of offset forging, that is what is shown here in the schematic. Frictional shear stresses develop at the die contact surfaces. So, these are the frictional shear stresses. Okay. So, that is developed because between the die contact and the die and the workpiece contact interface, and so these surface shears oppose the metal flow, creating resistance. So, here also we will introduce the concepts of sticking friction and sliding friction. So, what happens during this forging processes. So, here basically there is a neutral surface that exists which travels through the central line of the workpiece that is getting forged, and so if I draw it over here. So, so assume that this is getting pressed a cylindrical workpiece between two anvils or the between two presses. So, in that case, so up to a certain region from the central line there will be the zone for sticking friction, sticking, and the rest of the zone will be the sliding friction. Okay. So, this is the concept. So, and the neutral surface of the workpiece travels through its central line. So, this is how it works and how it guides the mechanism, guides the stress strain evolution and the deformation process that we will discuss now. So, this so the frictional shear stresses develop at the die contact surfaces, as we told, directed toward the central line, and so these surface shears oppose the material flow, creating resistance to deformation. Imbalance of force. So, due to the frictional stresses there is an imbalance of force in the x direction, that happens. So, this is we are talking about x direction, and so this imbalance must be compensated by a change in lateral pressure sigma x across the element. And then, so the assumptions here are the plate is assumed to have a unit width normal to the plane of the figure. So, that is the normal to the plane of the figure. So, that is what I told you at the beginning. So, this is the basic assumption, that is why we are considering the problem as a plane strain problem. So, the width of the plate remains constant during the entire deformation process. Okay. So, there is only change in the thickness and there is only change in the length. So, width remains the same. So, basically as we know that in case of metal forming the volume remains conserved. So, because the volume conservation, so that is why width is not changing. So, that has to be compensated by the length increase in length and decrease in thickness. So, that the total volume remains the same before and after the deformation process. So, taking the equilibrium of forces in the x direction. So, we can get, so you can see that this sigma x, that is the lateral pressure, it is acting towards the positive x. So, sigma x into the height of the workpiece that is getting deformed, so h. So, sigma x into h minus so this is the opposing the reaction stress that is getting generated, and for a I mean elemental thickness of dx. So that is why we are focusing our attention in this I mean derivation on this infinitesimal I mean width of the I mean thickness of the plate. So that is dx, and then I mean I mean here. So it is the opposing stress is sigma x plus d sigma x. So that is multiplied by the height of the workpiece, that is h. So this is what we are getting by balancing the equation at x direction. So sigma x into h minus sigma x plus dx into h minus, because this is the shear stress that is generated at the interface of the die and the workpiece, and that is opposing the deformation process. So that is a negative sign, that is why the negative sign is coming. So minus 2 tau x y dx into 0. So if we solve this equation, what we get? So sigma x h minus sigma x h minus d sigma x into h minus 2 tau x y dx is equal to 0. So sigma x h cancels. So then it becomes d sigma x into h is equal to minus 2 tau x y dx. Okay. So then from here we can get d sigma x by dx is equal to minus 2 tau x y by h. Okay. So the von Mises yield criteria, now we will apply the von Mises yield criteria, because this is a case of plane strain. So in case of plane strain problem, so it is the expression for von Mises yield criteria becomes the as shown here. So here sigma 1 and sigma 3 are the two principal stresses, where sigma 1 is the I mean dominant or the principal stress with higher stress value. So sigma 1 minus sigma 3 becomes equal to 2 by root 3 sigma 0. So sigma 0 is the ys, that means the yield stress of the material, is becomes equal to sigma 0 prime. Okay. And so because we are here not concerned about the y direction, because we told that there in that direction there is no change in strain, and because strain is responsible for generation of stress. So we were not bothered about the stress in the width direction. So we are bothered about the stress in the I mean longitudinal stress and also the vertical stress. So that is x sigma 1 here is the longitudinal one, and sigma 3 is the vertical one, that is the z direction. So that is so now so then if we define P and sigma x as positive compressive principal stresses, and then P is equal to sigma z, that is the vertical I mean compressive principal stress. So that is what you can see over here. So P becomes equal to sigma z. So then we can write sigma x minus P I mean or we can I mean write in opposite way, that I mean if we equate sigma 1 as z I mean so then sigma 1 is equal to sigma z, it becomes equal to P, because here P is dominant compared to the I mean stress in the I mean longitudinal direction, because that is the I mean pressure that is applied by the die to the workpiece, and the stress in the I mean longitudinal direction is getting generated because the applied I mean force by the die. So I mean and because the upsetting movement of the die. Okay. So then sigma 1 is equal to sigma z is equal to P. So then we can write that P minus sigma x. So as we told that we are not bothered about sigma y, because it is a plane strain problem. So we are only bothered about the I mean vertical stress and the longitudinal stress. So P minus sigma x is equal to sigma 0 prime. So that is we have shown earlier that it is based on the von Mises energy criteria. So from this expression we are coming to this expression. Okay. So since sigma 0 prime does not change with x, because this is a material property, that is ys. So then I mean so here it does not change with the space. So that is why it does not have a directional property. So then dp dx. So we can now we can get the derivative of this expression. So if I do the derivative, that means dp dx so dp dx minus d sigma x dx is equal to, because this is a constant term. So that is why derivative becomes 0. So then we get dp dx from here, dp dx is equal to d sigma x in by dx. Okay. And so if we substitute this in the previous equation, so that is the equation that we have written over here, that is d sigma x dx is equal to minus 2 tau x y by h. So, we from here we are getting the value of d sigma x dx. So, then we can write using these two expressions that d sigma x dx is equal to dp dx. So, here we have d sigma x dx. So, then we can write dp dx is equal to minus 2 tau x y by h. Okay. So, this is what we are getting from this expression and the previous expression. So, then if the shearing stress is related to the normal pressure by Coulomb's law of friction, sliding friction, which is tau x y is equal to mu p. So, mu is the coefficient of friction over here, tau is the interfacial shear stress and p is the applied pressure. So, then this equation becomes, so if we substitute tau x y is equal to mu p over here, then we get dp dx is equal to minus 2 mu p by h. So, from here we can write dp by p is equal to minus 2 mu by h into dx. So, this is what is we are getting. So, now if we do the integration, so then integrating both sides, we can get, so dp by p is equal to ln p is equal to minus 2 by h, I mean it comes out. So, 2 mu by h. So, then we get minus 2 mu x by h plus ln c, the integration constant. Okay. So, this is the expression we get by integrating both the sides. So, the constant of integration c is evaluated by the boundary condition that a free surface at x is equal to a. So, we are talking about this condition. So, when x is equal to a, so this is the x direction. So, when x becomes equal to a, for this limiting boundary condition, we can write that lateral stress sigma x is equal to 0, because in this condition this is at the boundary, as I have drawn in the previous slide also, that this is the case where the sliding friction completely prevails. So, the material is allowed for free movement, free lateral expansion, and hence the stress generated is 0. So, that is why the lateral stress sigma x is equal to 0, and then p is equal to sigma 0 prime. That means, the pressure value becomes equal to the, I mean, von Mises yield criteria. So, then it becomes equal to sigma 0 prime. So, this is also introduces the concept of friction hill that we will be discussing next. So, for now, if we put these values in this equation, so then what we get? We get ln p is equal to minus, so x is equal to 0, I mean p is equal to sigma 0 prime at I mean x is equal to x is equal to a. So, minus 2 mu a by h, okay. So, plus ln c. So, here p we have to substitute as p is equal to sigma 0 prime. So, then ln sigma 0 prime. So, then what becomes ln, so then ln c becomes equal to ln sigma 0 prime plus 2 mu a by h. So, now we have evaluated the value of the integration constant ln c, and then again if we put that value of ln c in this previous expression that we have got over here. So, then if we put the value of here ln c over here, so then we get ln p is equal to 2 mu x by h and plus ln sigma 0 prime plus 2 mu a by h. Okay. So, then this is the resultant expression we got. So, then what it becomes? So, then from here we can write that, so we can, so there is a space. So, here if we can write, so then we can get like, I mean ln p minus ln sigma 0. So, that means ln p by sigma 0 prime is equal to 2 mu by h a minus x. So, this is what the expression you can see over here, and then if we then from here we can easily write p by sigma 0 prime is equal to exponential 2 mu a minus x by h. Okay. So, this is, so then from here we can easily write that p is equal to sigma 0 prime into exponential 2 mu a minus x by h. So, since mu is usually is a small number, we can use the expansion Taylor series expansion. I mean, so then uy e to the power exponential to the power y is equal to 1 plus y square by 2 factorial by y cube by 3 factorial. So, accordingly we can easily write over here neglecting the higher order term. So, we are only focusing on 1 plus y, and here y is basically equal to this function. So, then it is p is equal to sigma 0 prime 1 plus 2 mu a minus x by h. So, this is the resultant expression for the applied pressure over the workpiece. So, then what is the average pressure? So, average pressure we can get the total forging load, average pressure need to be calculated from the average pressure. So, the average pressure is integrating the expression for P that we have evaluated here. So, integration 0 to A P dx by A. So, from here we are getting the resultant expression as this sigma 0 prime into e to the power 2 mu a by h minus 1 by 2 mu a by h. So, the total forging load P now can be established since P is equal to P bar, that is the average the average pressure into 2 A into W. Okay. So, where W is the width in the direction normal to the plane of the paper, which is not changing by the way, as we have told in the beginning. So, then the equation small p can be written. So, this is the expression for small p that we have established over here. So, then it can be written like, so p is equal to sigma 0 prime mu L by h into 1 minus 2 x by L. Okay. So, how we are writing as, so then basically we are considering here L is equal to 2 A. So, then if we put the value L is equal to 2 A, so then we can write here, you can from here. So, if I write that expression over here for your ease of understanding, so P is equal to sigma 0 prime exponential 2 mu A minus x by h, 2 mu A minus x by h. So, and we are assuming L is equal to 2 A. So, then we can write sigma 0 prime e to the power mu L and then here it is 2 mu x by h. Okay. So, from here we can write sigma 0 prime e to the power mu L by h. If we take common, then we can write 1 minus, so here 2 mu L by h we have taken common. So, then we have to write 2 x by L. So, this is the resultant expression, that is what we are getting over here. Okay. So, this expression is coming from this previous expression by putting the value of L as 2 A. So, this is the resultant expression for the pressure applied over the workpiece during offset forging. So, the pressure and stress distribution. So, the pressure distribution equation becomes P is equal to sigma 0 prime e to the power mu L by h into 1 minus 2 x by L. So, it describes how pressure varies along the length of the plate and with the depth due to friction and geometry of the material. So, this shows that as the plate's length to thickness ratio L by h increases, the resistance to deformation also increases. So, that means, so assume that if we are doing offset forging of a thinner plate. So, that means L by h ratio, so if this is the L and this is the h. So, then you can see that L by h ratio certainly will be the value of L by h ratio whatever it will become if we try to deform a much thicker plate. So, in that case L by h ratio will be smaller. Okay. So, that means what implies. So, in this, so if I mark it as L1 H1 and this one as L2 H2. So, then so the ratio of L2 L1 by H1, if the length are same. So, L1 L2 is equal to L. So, then if we can designate it as L. So, if I write that L1 is equal to L2 is equal to L. So, then L by H. So, then L by H1 will be much greater than L by H2. Okay. So, that means that in case of thinner plates, so L by H ratio increases and the resistance to deformation also increases. So, highlighting the importance of geometric factors in forging. So, a direct application of this L by H ratio we can see in case of flash forging that we have discussed earlier. So, where we keep the flash deliberately, so that we can maximize the pressure applied onto the workpiece by the die cavity, and we can get the impression of the die cavity obtained. The part can be made with the desired part geometry. Okay. So, then now here comes the friction hill. So, the concept of the friction hill refers to the build up of stress to a maximum at the plate center caused by friction between the die and the material. So, this stress accumulation forms a peak, a hill in the stress distribution profile, which is crucial for ensuring material flow and filling the die cavities effectively. So, this is the region where the sticking friction prevails, and this is the region where sliding friction prevails. Okay. I will write again for your ease of understanding. So, this is the case where sliding friction prevails in the workpiece, and this is the region where sticking friction prevails in the workpiece. Okay. And the transition between sticking to sliding friction happens somewhere in between. So, how to determine that region we will discuss next. So, this stress accumulation forms a peak hill in the stress distribution profile, which is crucial for ensuring material flow and filling the die cavities effectively. So, at the central line, that is neutral surface, the material flow is affected by the vertical and horizontal motions of the forging process, influencing how metal displaces and where stresses concentrate. So, impact of neutral surface. The neutral surface acts as a stationary point where the material flow changes direction. So, metal flows outward from this point. Okay. Understanding the location and behavior of the neutral surface is vital for predicting material flow and ensuring optimal die filling, especially in case of complex geometries, where by the way defining the neutral surface becomes difficult, and that is also a reason that is why we are not capable of solving the stress and strain distribution, the deformation conditions analytically, and hence we need to resort to the numerical tools, and that is why the essence of process modeling, essence of this course lies there for actual part geometries, complex geometries. So, the linear pressure distribution, the pressure distribution is linear with the distance from the central line of the slab during the forging process. So, that is what is shown over here. So, you can see that at the center the pressure becomes equal to the expression, that is sigma 0 prime e to the power 2 mu a by h, that we have discussed just in the previous slide, and at the edges of the workpiece it becomes equal to sigma 0 prime, that is the as per the von Mises yield criterion applied to the plane strain cases. So, sigma 0 prime is what? Sigma 0 prime is nothing but 2 by root 3 sigma 0, that means it is yield stress of the material multiplied by 2 by root 3. So, that is sigma 0 prime. So, this is how we can understand the concept of friction hill. And then the sliding friction limit. So, there exists a sliding friction limit at the die workpiece interface, so below which sliding friction cannot be sustained. So, once this limit is exceeded, interfacial shear occurs at the workpiece. Interfacial shear stress. So, the interfacial shear stress occurs at a value corresponding to the flow stress of the material, which is defined as tau y is equal to k. Tau y is the interfacial shear stress, where k is the yield stress in shear, and it can be expressed as sigma 0 by root 3. So, that means sigma 0 is the yield stress under tensile loading, sigma 0, and then it is sigma 0 by root 3, that is k is equal to ys under shear. Okay. So, this is the difference. So, there is different ys applicable in case of shear loading. So, where so general case for friction, in the general case the interfacial shear stress can be expressed as tau y is equal to mk. So, this is the concept which is differs from the Coulomb's friction model, where we have earlier defined tau shear stress, interfacial shear stress equivalent to mu p. But here so the interfacial shear stress can also be expressed as a multiplication of m into k. So, where m is the friction factor. So, for sticking friction, for the specific case of sticking friction, the friction factor m becomes equal to 1, and that means the material is stuck. I mean it is stuck at the die tool die and workpiece interface, and then this results in a maximum results to sliding, meaning the workpiece sticks to the die surface until deformation occurs. And so another way so that is what is I was telling, other than Coulomb's law, which states tau is equal to mu p. So, that to describe the interfacial shear is with the interfacial friction factor, that is tau is equal to m k. So, so substituting tau x y into m k in the previous equation, please recall that we have already evaluated earlier the expression for dP by P is equal to minus 2 mu by h into dx. So, before that we have evaluated dP by dx is equal to minus 2 tau x y by h. So, if we come back to that, okay, so what was the expression? Expression was dP dx is equal to minus 2 tau x y by h. So, dP dx is equal to minus 2 tau x y by h. Okay. So, now if we put the value of tau over here, so then it becomes minus 2 m k by h into dx. Okay. So, then we know earlier we have mentioned that in case of shear sliding friction or normal friction conditions, the k, that means it becomes equal to the yield stress in shear. So, then we can write that dP is equal to minus 2 m by h into this is sigma 0 by root 3, sigma 0 by root 3 into dx. Okay. So, as we have discussed earlier, the 2 sigma 0 by root 3 is as per von Mises yield criterion, we can express it as sigma 0 prime. Okay. So, then it becomes equal to minus sigma 0 prime m into dx by h. Okay. So, that is, and now if we integrate this expression, so then we get integrating both the sides like this. So, we get P equal to minus sigma 0 prime into m x by h plus integration constant c. So, again we will put the limiting value. So, in limiting value x is equal to a, p is equal to sigma 0 prime, that we know from the friction hill. We have seen that at x is equal to a. So, here it is the x direction. Okay. So, that x is equal to a, sigma is equal to sigma 0 prime, that is true for both positive x and negative x. So, that is why if we put the value of x is equal to a, p is equal to sigma 0 prime in this expression. So, then we can evaluate the value of the integration constant. So, then we get that sigma 0 prime is equal to minus sigma 0 prime into m a by h plus c. So, then c becomes equal to sigma 0 prime plus sigma 0 prime into m a by h. So, this is the expression that we get for c, for x is equal to a and p is equal to sigma 0 prime. Then putting the value of the constant back into this expression that we have just shown at the top. So, then from here we can again write p is equal to sigma 0 prime m into x by h. So, we can write p is equal to sigma 0 prime m x by h plus, we have already evaluated the value for the integration constant, that is sigma 0 prime plus sigma 0 prime m a by h. Okay. So, this is the resultant expression for p. So, then if we take from here, we can take common sigma 0 prime by into m by h. So, then it becomes equal to so plus c. So, plus p is equal to sigma 0 prime m x by h plus sigma 0 prime plus sigma 0 prime into m a by h. Okay. So, this is what we have got. So, if I take this one as common, and so there is a minus sign, so there is a minus sign that I have missed. So, then it becomes then it becomes sigma 0 prime m by h, means from here it comes a minus x plus sigma 0 prime. Okay. So, then so the expression for P becomes this one, that is what is written over here. From here we can write P is equal to sigma 0 prime. If we take sigma 0 prime as common now, so then a minus x by h plus 1. Okay. And where m is equal to 1, that means we are considering the case of a I mean sticking friction, where m is equal to 1. So, in that case the mean forging pressure is becomes equal to P bar is equal to sigma 0 prime a by 2 h plus 1. Okay. So, frequently the friction conditions are intermediate between full sticking and slipping, so that there may be a sliding friction at the edges of the plate near x is equal to a, where the pressure is lower, but at some distance closer into the neutral surface the pressure increases to a point where tau x y is equal to k, that is the yield stress under shear, that is sigma 0 by root 3 is equal to sigma 0 prime by 2. So, that you can easily understand from here. So, as we know that 2 sigma 0 by root 3 is equal to sigma 0 prime as per the von Mises yield criterion for plane strain condition. So, because we are multiplying here by 2, so if we put half over here, so we can write sigma 0 prime by 2. So, that is what we have written over here. And so, the distance measured from the central line where this transition occurs is x 1. So, at this point where the shear stress tau x y equals sigma 0 prime by 2. So, and in that case so we can write that the location from here we can identify the location of transition between the slipping and the sticking friction, x 1 is equal to a minus h by 2 mu ln sigma by 2 mu. Okay. So, so with this we have discussed the forging in plane strain in depth, and so we are stopping for this class here, and in the next class we will be discussing about rolling problems, different kind of rolling mills, and also the mechanics of rolling processes. So, till then, goodbye. Thank you.